Hello everyone. So in this video, right, we look at refraction through a rectangular glass slab. Now before we'll go to the rectangular glass slab refraction phenomena, we should have taken a look at the refraction that will happen at a plane surface. This already I'm assuming you would have seen in our previous videos. So whenever we have light ray that is incident at a plane interface, then depending upon the nature of the two medium, right, like say for example in this case we have the light rays moving from a rarer medium to optically denser medium, then what we would see is that the light ray will be bending towards the normal. If it is moving from denser medium to rarer medium, means it will be bending away from the normal. So this idea we already seen in the previous video. So in this video we will look at the important derivations on the refraction through a rectangular glass slab. So if you look at a rectangular glass slab like this, right, let us say we are incidenting a ray. Now what would happen is, so this is the normal line, there will be a bending. So here if you assume that this side we have air and this is the glass material is what, optically denser. So the light ray, right, would be bending towards the normal. It will bend towards the normal, and let's say this is the path of the light ray in the glass. So this is the incident angle and this is the R. Now this is where we have the first refraction happening at the boundary 1, and there will be the second refraction happening at the boundary 2. So boundary 2 is another plane surface. Here the refraction is happening from the glass towards the air. So which means what, if you take a normal over there, if you consider the normal over there, right, then when the refraction is happening, the light rays will be bending away from the normal. So which means they would bend away from the normal. We can represent the path like this. So they would be bending away from the normal. So here if you try to extend the normal line, by symmetry, this normal line and the other normal line, let us call them as normal line 1, normal line 2, both are what, parallel, right? Both are after all normals drawn from surface 1 and surface 2. Surface 1 and surface 2, this is the rectangular glass slab, right? Both the surfaces are what, parallel. So the normal 1 and normal 2 also will be parallel, which means the R angle marked over here will be same as the angle R. Okay. So we have two parallel lines and there is a transverse. The angle over here will be equal to the angle over here. Okay. Now what do we call them as? We'll call them as alternative interior angles, right? So alternative interior angles will be same. Here if this angle is R and let us say this angle over here is E, the final angle with which the ray is emerging, that's why we are calling it as what, angle of emergence, represented by the symbol E. Now we know that air refract index is 1, glass, let us say it is mu. This side also we have air, means refract index is 1. At the first refraction, when we apply the Snell's law, what do we have? Sin I by sin R is equal to what? Mu by 1. So which means sin I is equal to what? Mu times sin R. Let us keep it as expression 1. Then we'll apply the Snell's law in the second refraction case. Second refraction case is what? The refraction at the second plane surface, right? Here if you look at it, the incidence angle is what? R, because the incident ray is making an angle R with the normal. The refracted angle is what? E. So look at this Snell's law. Sin R by sin E is equal to what? Here the second medium is air. Divided by first medium is what? It is the glass. So here we can see what we will be having. If you rearrange them, we will have mu, let us bring it to the left side, mu into sin R is equal to sin E. Let us call it as expression 2. Now what we will be able to observe is, from expression 1 to expression 2, what is mu times sin R? That is sin I in the first expression. What is mu times sin R from the second expression? It is sin E. So what we will be able to conclude? We can conclude that Sine I is equal to sine E. So if the sine values are equal, we can say that the angles also will be what? Equal. So which means what? The angle I is equal to angle E. So here the angle made by the original incident ray with the normal is same as the angle made by the final emergent ray with the normal too. And we should keep in mind that normal 1, normal 2 are what? Parallel, which means the original incident ray here. This is the original incident ray, right? This original incident ray and the final emergent ray. The final emergent ray, they both will be what? Parallel. They both will be parallel to each other. So whatever the bending that is happening at the first boundary, that is exactly compensated because of the refraction at the second. Like say first refraction, what is happening? It is bending towards the normal by some amount. Second refraction, it will bend away from the normal by the same amount. So that overall, what do we see? The original incident ray and the final emergent ray, they both are what? Parallel to each other. Okay, so this is about the refraction through a rectangular glass slab. Now, while the incident ray and emergent ray are parallel to each other, what we see is that there will be a shift. So if you look at the path of the original incident ray, this is the path of the original incident ray, and this is the path of the emergent ray. So you will see that there will be a shift. Both are parallel, but there is a shift. So this sidewise shift is what we call as lateral shift. The sidewise shift that is happening is called as what? Lateral shift. So we'll see how do we measure this lateral shift value. So look at this. We have the incident angular I, and the angle inside the glass is R. The first refraction happens here, and second refraction happens in the second boundary. So if you see this, right, this is the emergent ray, and we know that angle E will be equal to what? I only. So the perpendicular distance between these two parallel lines, here we can see this is what? It is represented by the value Mn. Mn represents what? Perpendicular distance between the two lines. So when we say two lines, what are we talking about? The original incident ray and the final emergent ray. This perpendicular distance is what we are calling as the lateral shift. So we'll try to find what is this value of Mn. We'll have to find what is the value of this Mn. Look at this Mn, right? So Mn, the way we'll look at it, it will be perpendicular to both the line 1 as well as line 2. Okay. Now we can see, if you mark this point as say O, triangle OMN is a right angle triangle. Triangle OMN is a right angle triangle. In this you can see, this is the original path of incident ray, means the way we are marking the angles, right, this R plus delta will be equal to I, which means delta will be equal to what? I minus R. What is the angle delta here inside the triangle OMN? The angle delta will be equal to what? I minus R. So R plus delta will be I. So delta will be I minus R. So in this, right, the Mn value and hypotenuse is OM. Look at this, the sine delta. What is sine delta? It will be Mn by opposite. Mn by hypotenuse is what? OM, which means OM into sine delta. That is our Mn. Sine delta means what? OM into sine of I minus R, that is Mn. So here we are understanding that we will be knowing what is the value of I, and we will know what is the value of R. In this, the only unknown thing is Mn, OM. Only unknown thing is what? OM, right? So let us try to get what is the value of this OM. Because if you are able to get the value of OM, means we have got our lateral shift value. Okay. So we'll see how do we get the value of this OM. Now for getting the value of this OM, right, we will look at another triangle that we can think of. So the triangle is, if you draw a perpendicular, the same line, basically the normal line. Okay, so we'll extend the normal line, and let us say this is touching at a point P. Now look at this triangle OPM. This is also right angle triangle. Triangle OPM is what? Right angle triangle. So here, we'll just write down the expression that we got. The MN value is equal to what? OM into sine of I minus R. Okay. Now we are looking to find what is the value of OM. Because if we are able to get the value of OM, means we have got our answer for MN. Because MN is what we are trying to find, right? The perpendicular distance between both these parallel lines. In triangle OPM, it's a right angle triangle. OP is the thickness of the slab. OP is the thickness of the slab. Okay. And here we see that there is an angle R. And it's a right angle triangle, right? So in this triangle, what is cos R? Cos theta will be what? Adjacent, which is OP, divided by hypotenuse. Hypotenuse is same. What is it? OM. Which means OM will be equal to what? OP by cos R. OP is what? T. Into 1 by cos R means what? Secant R. So OM is what? OP by cos R. We can write it as what? OP is T. 1 by cos R we can write it as what? Secant R. Now as it is, we'll just have to go and substitute. So what is the MN value? Finally we are getting MN is equal to what? T times secant R sine of I minus. So this is what is the lateral shift. What is it? T times secant R into sine of I minus. So this is what is the perpendicular distance between the two parallel lines. One is the original incident ray and second is the final emergent ray, and that is what we also call as the lateral shift. Now while we have lateral shift for a single ray that is incident on a rectangular glass slab, if we have either converging rays or diverging rays which are passing through the rectangular glass slab, means if a glass slab is placed in the path of the converging or diverging beam of light rays, right, then what we will see is that the point of convergence or the point of divergence, means the point to which they should be converging or the point to which they should be diverging, that will get shifted. And this is what we call as the apparent shift because of the rectangular glass slab, and this shift is referred to as the normal shift. Why? Because here we look at the shift happening along the normal line. So when we look at the position, right, the position is getting shifted. Let's say for example we have the object here O. Light rays are coming from the object. They get refracted twice, and we'll see that this is the final emerging ray from the rectangular glass slab. So they appear to come from a point O dash. Really the light rays are not coming from O dash. They appear to be coming from the point O dash. So it will appear to somebody who is viewing that the actual object is at O dash and not O. So this shift is happening along the normal to the, so this is the normal line, right? The line is what? To the rectangular glass slab, this is the normal line. The shift happening along the normal is what is called as normal shift. Normal shift will come when either a beam of converging rays or diverging rays, they are incident on the rectangular glass slab. So the point of convergence or point of divergence, right, that appears to get shifted, and we will measure the shift along the normal line. That's the reason we call it as what? Normal shift. Okay, and this normal shift value, right, will be dependent upon the refractive index value of the glass slab. It will depend upon the thickness, and we'll see how do we get the expression for the normal shift. So whenever we talk about the refraction through a glass slab, right, so one is the lateral shift. For a single ray of light, it will have a lateral shift. But when we look at the converging rays or diverging beam of rays, the point of convergence or point of divergence, it appears to get shifted, and that's what we'll refer to as the normal shift. So we'll see how do we measure this normal shift value. So consider the situation where we have a glass slab here whose thickness is T, and the material of the glass slab, let us say the refractive index is mu. Okay, so here this AB, right? AB is what? The thickness of the glass slab. Now we are keeping our object at the point O. We are keeping the object at the point O. So look at this. The ray will first come and incident at point M. That will get refracted. So after the first refraction, right, the ray appears to come from a point I1. After the first refraction, the ray appears to come from point I1. Means if you are observing from here, from within the glass slab, right, to us it will appear as if the rays are coming from point I1. In fact, this is what we have talked about when we are seeing objects by staying inside a denser medium. So like, if you are staying in water and we look at an object which is at the top, we have said, right, the apparent height will be more than the real height. So here in that sense, right, the real position of the object from the surface 1, let us call it as x. So we are saying OA is equal to what? X. OA is the real position. Now the apparent position, which is what? AI1. AI1 will be the apparent position. Apparent position will be what? This is like apparent height. Apparent height will be what? It will be mu times the original height. So this is something that we have already talked about in the case of the apparent height. When we are seeing things from denser medium to the objects in a rarer medium, right? So what we see is that things will appear to be farther from their actual position. Okay. So AI1 will be equal to what? Mu times of x. Now this ray, right, is going and incidenting at point N. This is getting refracted. So this appears to come from point I. This is our final image position. This I is basically our final image position. Okay. Now over here, right, we will have to measure the distances from the surface 2. We will have to measure the distances from where? From the surface 2. So here if you look at the position of the light rays. So after the first refraction, the light rays appear to come from point I1, right? So position of the light rays will be what? It will be BI1. And what is BI1? It is what? BA plus AI1. So BA is what? T plus AI1 is what? Mu times x. The position of the actual light rays, they appear to come from I1, right? So what is it? It will be what? BI1. We have to measure the distance from the surface 2. BI1 will be equal to what? Mu times x, which is our AI1 plus T, which is AB. Now after getting refracted, the final rays appear to come from the point I. So which means this BI value, right? So here when we are observing from the rarer medium. BI value will be equal to what? BI1 by mu. It is like we are seeing the apparent depth. The real distance, which is BI1 divided by mu. That is what is going to be the BI value. Okay. So what is this BI value? It is BI1 by mu. So BI1 is mu x plus T divided by mu. So we'll just split the term. It will be what? X plus T by mu. So BI value will be equal to what? X plus T by mu. Now we got the BI value. What is our final task? We are looking at the normal shift. You know what is normal shift here? What is the normal shift here? The OI. What is the normal shift? This is the original object, right? The final image appears to be here. This OI is what is our normal shift. Now let us see how do we get this OI value. If you see OI can be, this is a little bit of a mathematical simplification that we are doing in terms of the distances. OI can be expressed as OB minus BI. So OI can be expressed as what? OB minus BI. OB, further we are writing it as what? AB plus AO. what is AB? AB we know. What is AB? It is the thickness. OA is what? X. BI already we got it. So just substitute them. AB is what? Thickness T. OA is that is the original position of the object from the surface 1. Minus BI. What is BI? X plus T by mu. So here we can see this is what? T plus X minus T by mu. So plus X minus X is cancelled. We'll take a T common outside, means we'll have what? 1 minus 1 by mu. So what is this OI? 1 minus 1 by mu into T. So this OI is what we'll be referring to as the normal shift. That's it. So the normal shift is what? The distance by which we will see that either the point of convergence. So here we have done the derivation by using the idea of point of divergence, but for the point of convergence also similar relation will come. The value by which the point of convergence or point of divergence will be shifting, and we will measure the shift along the normal line to the slab. That is why we call it as what? Normal shift. So what is the normal shift value? 1 minus 1 by mu into T. Okay, so this is about the refraction through a rectangular glass slab.